Welcome back. This is Dr. Pierce again, and we are going to pick up with the following section as described in Learning Objective 4, which focuses on urine concentrating abilities. In order to really grasp how urine concentration occurs, we need to begin by introducing or reviewing the interstitium of the kidney. So the interstitium of the kidney is defined as the space between all of the tubules, glomeruli, and vessels. And the space between all these things isn't just empty space. It does contain a number of cells, such as fibroblasts, and those fibroblasts are the source of erythropoietin, extracellular matrix, and the interstitial fluid. Over here on the right, you can take a look at this histological staining of cross-section of the kidney where you see the round structures of the tubules and you see lots of cell types, and there's a key down here that kind of tells you what it is you're looking at. But there is a little bit of a misconception that the space between tubes is all kind of scrunched up together, and that's because when we take a kidney that is from dead tissue and then process it, or even a kidney biopsy sample, the processing itself will kind of suction out all the space between cells, all the fluid part. And so there is left with what was tubules that have just a little bit of space between them. They all get scrunched up. And so that's kind of what this picture shows. But really, in real life, there is space between all of this. It's not a lot of space, but there is space. And so this graphic on the right is depicting what that is probably in a real living tissue that hasn't been taken out for processing, what it would really look like. And so you can see that there's space between tubules and glomeruli and vessels. And this space, as I said, isn't just empty. It does have some cells that fill it. It has some micro vessels as well, and it has fluid. And this fluid is probably not, necessarily what you think of as watery fluid that pours and flows like a river, but it's more like extracellular fluid. So that extracellular fluid is what we're going to be talking about because this ECF and the osmolality of the interstitial extracellular fluid is going to impact how we concentrate our urine. And then furthermore, if we look at this kidney over here on the left, this is a sectioned out real kidney. I think this one was from mouse. I don't quite remember, but I think it was from a mouse kidney. But as you know, there's the cortex and then all the way down to the medulla of the kidney. And this area of the kidney actually has interstitial fluid flowing throughout all of it because, again, it's that space between everything. But that interstitial fluid has different concentrations of osmolality depending on where you are. So up near the cortex, this is closest to where the glomeruli would be. And you have your stuff, you have your distal convoluted or your proximal tubule, and then you have your loop of Henle that flows down to the medulla, and then it comes back up, and then you have your distal tubule, and then eventually flows into a collecting duct. Okay, so the cortex of this kidney, the cortex of the interstitial fluid, which I'm going to put as ISF, has a smaller concentration of osmolality. So it has less osmolality. However, the deeper you go into the medulla of the kidney, towards the medulla, the ISF osmolality increases. and there is therefore a gradient. So it is the least concentrated in osmolality near the cortex, and it gets more concentrated as you proceed toward the medulla. And this is important because our loops of Henle plunge into the medulla, and that means that the area surrounding this loop of Henle, as it plunges deeper into the medulla, is going to be embathed in a more richly concentrated interstitial fluid osmolality. As we transition into discussing the mechanisms by which urine is concentrated, we're going to be talking about two types of mechanisms, and they are called the countercurrent mechanisms, specifically the countercurrent multiplier and countercurrent exchanger. And they're sometimes written as countercurrent multiplier and countercurrent exchanger as CCM and CCE. They are continuously ongoing processes, so it's not like they have a start and a stop time. They're always ongoing. Well, they're always ongoing, assuming there is no pathological condition. And it involves the interstitium, and we just got done talking about the medullary osmolarity and the gradient going from the cortex to the medulla, and that change in concentration gradient of the osmolality. So the osmolality at the cortex is lowest, and then as we go deeper into the medulla, the osmolality is the highest. And that gradient is a ongoing gradient that is continuous from the cortex all the way to the medulla. In order to keep straight all of our different areas, please continue to keep in your mind's eye. We're going to be talking about three spaces as we go on. The first space, or you could call these almost like pipes, is the tubular space. So this is the nephron itself. This is the proximal tubule, the loop of Henle, the distal tubule, and the collecting duct. That is the actual tubular space. Also keep in mind there is a separate space that is for the blood vessels. This is the vascular space. So these are pipes that essentially run along and alongside and with the nephron. So these are either the peritubular capillaries or the vasa recta. And then finally, we have the interstitial space, which is the space between everything else. Now, because we have fluid in all of these things, we have ultrafiltrate in the tubular space, we have blood in the vascular space, and we have interstitial fluid in the interstitial space. Everything has its own osmolality. And as we already mentioned, the interstitial space is special, that it has an osmotic gradient that changes from the cortex down to the medulla. Also keep in mind that fluid and solutes, they are always moving. There's always ultrafiltrate flowing through the nephron. There's always blood flowing through the vascular pipes. And then there's always interstitial fluid that's making up the space between everything else. So as we go into the next section where we start to talk about the countercurrent mechanisms, keep in your mind's eye that the fact that there is an osmolality in each of these pipes or the interstitial space, and that they will influence each other. The first mechanism we are going to talk about is called the countercurrent multiplication. The countercurrent multiplication moves sodium chloride from the tubular fluid into the interstitial space. It does this throughout the length of the kidney nephron from the outer part of the medulla deeper into the inner part of the medulla along the loop of Henle. Although in reality it is a continual process, the way the countercurrent multiplication builds up an osmotic gradient in the interstitial fluid is kind of broken up into two steps, the first of which is called the single effect. The single effect is driven by the active transport of sodium and chloride out of the epithelial cells of the thick ascending limb. And then as a result of sodium and chloride being reabsorbed out of the thick ascending limb into the ISF, the interstitial fluid becomes hyperosmotic. As a result of the interstitial fluid becoming hyperosmotic, what does water want to do? Well, water wants to follow. So it wants to try to bring that interstitial fluid back into equilibrium, into more of an isoosmotic state. And so what does it do? Well, it's going to passively leave not the thick ascending limb, because that's impermeable to water, but the thin descending limb, which it can move out of the thin descending limb because it expresses those aquaporin channels. So we have solutes leaving the thick ascending limb going into the interstitial fluid. And then we have water leaving the thin descending limb to try to help equalize that interstitial osmotic gradient. However, because this is not just a one and done kind of effect, there is constant fluid flowing through the tubule because we have a constantly active GFR. There is always new fluid entering the tubule from above. And since there's always new fluid entering the tubule from above, that will push what's below it on through the loop of Henle, on through the pipe. And as a result, the gradient will develop because of that constant kind of pushing downward. And the effect, meaning the effect of the hyperosmotic interstitial fluid, only multiplies the deeper and deeper you go. And this is, in fact, the process by which the interstitial fluid becomes most hyperosmotic is dependent on the anatomical length of the loop of Henle. So in this number one loop of Henle, we have a loop that is this long, and let's say that that sets up the deepest effect that you can get is a 1200 milliosmol per liter interstitial fluid, because there's only so much deeper that the fluid from above can push down before you get to that hairpin turn, and then goes back up again. But compare that to this second loop of Henle. Let's say it's much deeper and longer loop of Henle. Maybe now, because it's just so much longer, you can get 2000 milliosmol per liter, simply because it's just so much deeper and longer compared to this first one. So the length of the loop of Henle determines the size of the osmotic gradient in the interstitial fluid. Now we just got done talking about the countercurrent multiplier, and the countercurrent multiplier, unlike what we're going to talk about next, the countercurrent multiplier is about the interstitial fluid hyperosmolality. And that is developed because of sodium chloride moving out of the tubule into the interstitial fluid, and then water follows. Next, we're going to add onto this system a vasa recta. So kind of superimposed upon the loop of Henle is a long blood vessel called the vasa recta. So this is essentially part two of the countercurrent mechanism. And the countercurrent mechanism that we're going to talk about now is the movement of water from the interstitium into the vasa recta. So now we're going to talk about water moving from the interstitium, so the interstitial fluid, into the blood vessel. And the blood vessel we're specifically talking about is the vasa recta. If you look at this image over here on the right, this was a beautiful image of the loop of Henle and the nephron, and then the peritubular capillary and the vasa recta, drawn by one of your student doctor colleagues from the class of 23. She sent it to me, and I thought it was so beautiful and said that I could use it next year if I wanted to, because I'm not an artist, and I tried to draw this myself, and it just wasn't comparable to this beautiful image. But I really wanted to show it because you can't really find a good physiologic graphic that depicts this all ongoing at the same time. So let's look at this image. In the pink is the blood vessel. So that's this one here. So this coming in is the afferent arteriole. The afferent arteriole enters into the glomerulus. You have the bundle of glomerular capillaries, and then it leaves the glomerulus as the efferent arteriole. And then we have some peritubular capillary that is going to flow along. Peritubular capillary flows into the vasa recta that's going to follow the loop of Henle. So notice here that this blood vessel, the fluid in the blood is moving in this direction. All right, it's flowing down in this direction. And then the blood vessel fluid has a hairpin turn, and then it goes back up towards the cortex and on and then out, and eventually forms the renal vein. Now notice that the glomerulus and the Bowman's capsule that's coming off of it, the proximal tubule is kind of oriented in a opposite direction as the blood vessel. So the fluid that's being filtered, so this is where your glomerular filtrate is flowing into Bowman's capsule, then the fluid that's leaving this area into the proximal tubule, so this is the proximal tubule here, this fluid is actually flowing in a direction that's now going downward and downward towards the medulla. This fluid is flowing, notice, in an opposite direction from the blood vessel fluid. Now down here at the bottom, it makes the hairpin turn and then it goes up. And you'll notice that this is flowing in opposite direction as the blood vessel. So the blood vessel fluid is moving down, but the portion of the nephron that's right next to it, the fluid in that portion of the nephron is moving in the opposite direction. And this is what is the process by which this exchange of fluid, because we just got done talking about countercurrent multiplier, where you have solutes, in this case in the thick ascending limb. So this part right here is the thick ascending limb. The thick ascending limb is reabsorbing sodium chloride into the interstitial fluid. Meanwhile, water is leaving the thin descending limb over here. So this water will get reabsorbed into the blood vessel, the vasa recta, as it's moving upward. Meanwhile, over here on the left, there are solutes that are getting added to the vasa recta. So what happens if you add a bunch of solutes to the vasa recta? Well, if you are adding a bunch of sodium chloride to the vasa recta over here, but no water, then the deeper you go, the more sodium chloride it builds up until you have so much sodium chloride that you have at the bottom of the hairpin turn, the highest concentration you can have in the vasa recta. But now the fluid is pumping back up, it's going back up, and now water can enter because this portion of the vasa recta is running alongside the thin descending limb where there's water. The water is leaving the thin descending limb and it's getting pulled into the vasa recta. And what happens when you add water to something that has a high osmolality? Well, it's going to dilute it. So that's why as you ascend up the vasa recta, these numbers that represent the osmolality, these numbers get smaller because you're adding more and more and more water until you get back up at the top and you have essentially an isotonic fluid again. So the difference in this interstitial fluid osmotic gradient is going to impact the fluid in the tubule and the fluid in the blood vessel, such that the most concentrated you can get in either one is dependent on how long these loops of Henle's are. In humans, it's 1200 milliosmol per liter is the most concentrated you can get. And then another thing I want to bring up is that there is a impact of what we call the blood flow rate. So if in the vasa recta specifically, if blood flow is fast, then there's just not enough time for solutes and water to get reabsorbed. It kind of gets washed out. We'll talk about that next. But just know for now that blood flow, the rate of blood flow, will impact the equilibrating abilities between the vasa recta and the tubular fluid. So we just got done talking about essentially how the interstitial fluid gets its osmotic gradient that differs from the cortex all the way down to the medulla. And now we've added in that there is an exchange between the interstitial fluid and the vasa recta that will impact the amount of water that is reabsorbed or not reabsorbed. And so next we're going to talk a little bit more about urine formation. Before we get into urine formation, there's one more kind of a caveat I want to add about the interstitial fluid. So we've talked a lot about the osmolality of the interstitial fluid, and we've talked about sodium chloride. However, there is another solute that contributes to the interstitial fluid osmolality. The first that contributes to the actual number, so the number, say the 300 milliosmoles per liter, is half of that is contributed to, half of this 300 is contributed to by sodium chloride, and the other half comes from urea. So the medullary osmolality of the ISF, I'm going to put ISF, interstitial fluid medullary osmolality, is due to the presence of sodium chloride and urea. What this graphic on the right is showing you is there are numbers kind of outside in the white portions here. This is depicting the interstitial fluid osmolality. Interstitial fluid osmolality, interstitial fluid osmolality, interstitial fluid osmolality. Up near the cortex, this is essentially an isotonic fluid. It's around 300 milliosmoles. As you get deeper into the medulla, now you have a more concentrated interstitial fluid, now at 900. And then at the deepest portions, at the bottom of the loop of Henle, it's its most concentrated that I can get at 1200. But this 1200 is actually half sodium chloride and half urea. So that's why there's 600 plus 600, that equals 1200. Up here, the 600 is from sodium chloride and 300 from urea. And that's how you get 900. And then at the top, it is mostly from sodium chloride, and then the rest is from urea. So what that means is there is the most urea is at the bottom of the loop of Henle, or in the medulla. The innermost portion of the medulla is where the most urea is found. And that is because we talked a little bit earlier, so if you don't remember it, you can go back and kind of review how urea gets moved out of the collecting duct. So urea builds up its concentration because water, in the presence of ADH, water gets pulled out of the collecting duct and leaves behind and concentrates everything that's left behind. As a result, urea, by the time you get to the bottom of the collecting duct here, urea has such a difference that it's going to move passively down its concentration gradient into the ISF. And then it's floating around here at the bottom of this medulla, and it eventually encounters the loop of Henle again. And the loop of Henle sets up essentially a urea recycling, such that urea can get pulled back into the loop of Henle and just start the process over again. Okay? And so that is essentially how you get urea recycling. So urea just will recycle. It'll come back around over here again. You have ADH pulling water out, and then urea will build up again, and then it pumps out. So the more urea that flows down its concentration gradient from the collecting duct to the inner medulla ISF, the more concentrated this number can get until we reach a maximum of 1200. So in order to maximally concentrate the interstitial fluid and therefore maximally concentrate the urine, you need to have urea working alongside sodium chloride. And finally, putting this all together, this is showing the countercurrent exchange in the vasa recta alone. So this is blood, okay? This is not a nephron. This is just blood vasa recta that is following the loop of Henle. So you can see that this looks like a loop of Henle, but it's not nephron. This is a blood pipe. We have plasma flowing down the descending limb of the vasa recta. As the plasma flows down, the plasma or the blood is getting more and more concentrated. It's getting more concentrated because there are solutes being dumped into the vasa recta, and this consists of sodium chloride, sodium chloride, sodium chloride. Okay, so you're dumping more solutes into the descending portion of the vasa recta. Meanwhile, because the interstitial fluid is hyperosmotic, there is some water that is simultaneously leaving this part of the vasa recta. Not only is that going to contribute to the concentration of the blood, but this is a passive movement from the blood into the ISF, okay? But after the hairpin turn, solutes can leave the vasa recta again. Meanwhile, water is entering back in, and this is a diluting pattern. So in the descending portion, we have a concentrating pattern. And then in the ascending portion, we have a diluting pattern. Such that by the time we get to the top again, we have a blood that has diluted compared to where it started out down here at the bottom in the medulla. Now, if we did not have this U shape, so this U shape of the blood that follows the loop of Henle, if we did not have that, large amounts of solutes would be lost from the renal medulla. So what happens if, to urine concentration, if a patient is on a vasodilator, or if they have a large increase in arterial pressure? Well, certain vasodilators can have a result where it increases renal blood flow. An increase in renal blood flow, particularly as it's going through the inner medulla, so essentially the bottom portion of this vasa recta, it does what we call a washout. A washout means essentially that because of that increased renal medullary blood flow, some of the solutes from the renal medulla gets essentially washed away, meaning that it doesn't have time to leave the blood vessel again, okay? And so it just gets kind of sucked on up and out of the hairpin turn area. As a result, this will change the interstitial fluid concentration here in the interstitium, because if you don't have solutes leaving the blood of the vasa recta and returning to the interstitial fluid, then you don't have as a maximum number. You can't reach your maximum of 1200. And what that will do is it will reduce your urine concentration. Large amounts in blood pressure, like very high blood pressure, for instance, can also increase blood flow. So this increase in renal blood flow can be due to a vasodilator or just very high blood pressure. And that can also tend to wash out the renal medullary hyperosmotic interstitium and also reduce the ability to concentrate your urine. So essentially that is all I'm going to be talking about when it comes to urine concentrating ability. Big takeaways are that there are 2 steps to create the process by which urine concentration can occur. And they are the countercurrent multiplication, and countercurrent exchanger. And then that countercurrent exchanger involves this very specific anatomical orientation of the vasa recta, where you have blood flow flowing in opposite direction from the tubular fluid flowing through the loop of Henle. There is an exchange of solutes and water in and out of the vasa recta and the interstitial fluid. The length of the loop of Henle and the movement of those solutes, such as sodium chloride and urea, can determine the maximum concentration of the solutes in the tubular fluid. So if the maximum concentration is 1200, which is what it is in humans, then this is not only the maximum concentration in the blood at this portion, but also in the tubular fluid. What happens then in the collecting duct after this concentrated tubular fluid and blood ascends back up towards the cortex and goes through the distal tubule? What happens in the presence of, say, ADH is ADH will allow for water to get pulled out of the collecting duct. As water gets pulled out of the collecting duct, then the fluid in the collecting duct gets more and more and more concentrated until there is an equilibrium, again, as it passes through this deepest most portion of the medulla. And then this tubular fluid here, by the time it gets to the bottom of the collecting duct, is going to be in osmotic equilibrium with the interstitial fluid at that area. And if the interstitial fluid at that area is 1200, then the tubular fluid at the bottom of the collecting duct will also be 1200, meaning you will urinate out 1200 milliosmoles per liter concentrated urine.